So in this problem, we've got our component A reacting to give us 3 of B. So A diffuses in. So there's A coming in here. And for every 1 of A coming in, 3 of B are going out. And when we say coming in and going out, we also don't want to assume something here, right? Why do we say going out? Why doesn't B just sit on the surface, right? And why do we say A is diffusing towards the particle? So we want to be strict and not assume anything at all. So why is A coming towards the particle? Well, we know that near the particle, A is reacting. So right here, right on the surface of the particle, if you can imagine a tiny little subvolume here, right on the particle, A is being consumed, right? By the reaction, A goes to 3B. So A is being consumed. That means right near the particle, the concentration of A is going to be low. And so overall, we've got a concentration gradient with a low concentration here and a higher concentration out there. And we know that by diffusion, we are always diffusing against the concentration gradient. That means we are always going from high to low. So A must be going like that. And then we've got B, and B is only appearing near the surface because of that reaction. So B is being produced on the surface. That means we will have a high concentration of B near the surface. And we assume that we are starting without any product in the fluid. So there's a low concentration or a 0 concentration of B in the fluid, and there's a high concentration of B due to the reaction happening on the surface. So the net result is that B is going out like that. So the two things, the molar flux of A is towards the particle and the molar flux of B is away from the particle. And then we also need to define our coordinates. So if this is a spherical particle, then we are assuming, if it's a spherical particle, then spherical coordinates are suitable. And so we will define R to be the outward direction from the center of the particle. And these are all the things that we have to think about. None of this is trivial, right? I mean, we could have defined R from the surface of the particle going out, but from the center is a little bit more suitable, as we'll see. And then thinking about the directions of things, that's another thing that we have to pay careful mind to. And in fact, let's start working on this here. So let's save a new instance of this. So in our development here, we're going to say, well, we've said A is towards the particle. So we expect that our NA, so NA, we are expecting this is going to be negative. And we expect NB, the number that that's behind NB, that's going to be positive. And we also want to write something like NA equals something times NB. So we've got a 3 in there. And we know the signs will be different. So if we think about this, A gives us 3B. So we have 3 times as much of B being formed as A. So NB is 3 times as much as NA. And it's a minus, so it's a minus 3NA. And you can see that we did it wrong here. If you just go by the problem, it looks kind of automatic. There's A, there's 3B, so I've got NA, that must be minus 3NB. And that's the wrong way around, right? So it needs to be minus 3NA times NB, okay? And then we can go ahead and use our usual mole, our mole equation. Yeah, I'm not sure whether you want to do all this now. So I just wanted to point this out so we know that we have minus C. Akim, yeah.
So I just wanted to ask real quickly, over here for question A, it says, what is the surface reaction flux? But in previous questions, they were asking for the molar flux, so most of the time. So is there any difference between the two?
Right. So yes, there is a difference. You see, in these coordinates, in spherical coordinates, your area is changing as we move away from the particle, right? So at a given radial position, the area of interest is different. So what we mean by that is, if we want to estimate, let's say the total molar flow rate. So if we say dNA dt, and we want to know what this is at some position R, right? Then we could define this. We could say, I'd like to know what's the number of moles per second, right? Let's draw it here separately. So there's the particle. And then we just pick some arbitrary radial position and we say, at this position R, so here's R, at position R, I'd like to know what's the total molar amount of A that's crossing this boundary. And it's outside the particle and all of that, but I can still define R, and I can define a molar flow rate in towards the particle. So I can ask, what's the molar flow rate at this radial position R? And this is how I would define that. And then, of course, we could say the molar rate is going to equal the molar flux at position R. Write it like this. And so that's flux, that's on a per area basis. And then we need to multiply by the area there. So that's going to be 4 pi R squared, right? So that's the molar rate at R. And now at steady state, we are saying that at steady state, dNA dt is independent of R. So if that's true, then dNA dt at R, let me write it like this. Let's say at R1, dNA dt at R1, at position R1, that equals dNA dt at position R2, where R1 and R2 are any radial positions outside of the particle. So if that's the case, then we can say the molar flux at radial position R1 times the area at radial position R1. So there's the molar flux at radial position R1, and there's the area at R1. That must equal the molar flux at position R2 and the area at R2. So looking at this relationship, we can see here that NA at R2 equals NA at R1 times, and the 4 pi's can cancel on both sides. And then we're going to have here R1 squared, R1 squared over R2 squared. So you see, this does matter. The radial position does matter. Instead of calling it R2, I could have just said R, right? So then this would be R squared. So you see, your molar flux is changing with your radial position here, because our assumption is that the molar flux is not changing in R, it's uniform. The molar flow rate is not changing. So this comes from saying that we have a steady concentration profile. So if the concentration profile is steady, that means Na for all positions R, Na at all positions R equals all positions T and R, right? For all time, Na is constant. So we are saying that the number of moles is the that is changing in R, but it's not changing in T. And the only way for Na not to change in T is for dNA dt to be fixed. So there's no change in the rate of change of Na. So the reason we are saying all this is when we did the example in rectangular coordinates, right, we did have problems where we had a straight pipeline and we had our species diffusing, and sometimes it was equimolar counter diffusion and sometimes not. So we did say that we want to assume, number one, we said that the concentration profile was steady. And if it's steady, then that means that your, let's say if that's steady, then it means that your number of moles is not changing. So your concentration is not changing in time. And the only way for concentration not to change in time is if we have the same molar flux at each point, or the same, the rate of change of moles at each position. If you take a subvolume here, dNA dt is 0. So dNA, a lowercase a, number of moles. So the number of moles is not changing in time here. So for that not to change in time, then it must be the case that the molar flow rate is the same at all positions. So your molar flow rate is the same at all positions, and that means your flux is the same everywhere. But this was for in the Z direction. In the R direction, the area does change. In the Z direction, the area doesn't change, right? The area here is the cross-sectional area. So these cross-sectional areas are not changing as you change in Z. As you look at positions down this pipe, the cross-sectional area is the same. Whereas here, if your variable is R, as you look at different R positions, the areas are different. But the molar rate of change has to be the same, or the molar flow rate has to be the same. I should have used better symbols. I should have used FA instead of dNA dt. But we are saying that in this shell, for example, the rate of change of moles is 0, and then the molar flow rate, right? So we can say FA. Let's write it this way better, right? So we can say the rate of change of moles, so dNA dt, and this is going to be between positions. Let's say here R and R plus delta R. So between those two positions, the number of moles will change according to the flow into the space. So the molar flow rate of A at position R, so that's what's coming into the space minus what's going out. And this is going to be R plus delta R. So when we say the number of moles, if we say the concentration is steady, then that means the rate of change of moles between those 2 points, in the space between those 2 points, the number of moles there is fixed. So this is a 0. And if that's 0, then that means at each radial position, your molar flow rate is the same. So we can say here FA as a function of R is a constant. And FA being a molar flow rate is equal to the molar flux times the area at that point, 4 pi r squared. So that's constant, but as we consider different r values, then NA has to change accordingly. So the molar flux is not fixed in spherical coordinates. Does that answer it? Okay, so I just see in the chat, please upload the lectures. So I do periodically upload the lectures. One of the problems that I've felt in previous years is that then people stop coming to these sessions, and I rely on your questions to shape the session. So I will periodically upload, but then don't let the attendance suffer in these sessions either, right? Okay, so Akeem, did that answer your question there? Okay, any other questions or comments on this? Right, so I guess we've gone far enough into this that we'll do this in detail. So what is the surface reaction flux, we want to know. And let's look at what data is given to us. So we are given the diameter. Yeah, when it's said like this, we typically mean diameter, right? 5 centimeter particle, that means diameter, not radius. And then we are given the reaction, we are given the total concentration and the diffusivity. We have said that our, let's use our basic mole equation. So we know this is minus CdAb dxa dr. And then we've also got plus xa, and this is Na plus Nb. And we've said from this that the molar flux of B is 3 times the molar flux of A. So Nb is minus 3 Na, minus 3 Na. And so overall, this is going to be minus 2x Na. And so we can take this across to the other side and write this as Na into 1 plus, sorry, this is supposed to be a minus here, right? So it's minus 2n, and so this is plus 2 xa. That's the equation. And then we can see this is the variables xa. We have the variables xa here. And as we've said just now, Na is a function of radial position also. So now we need to account for that. And we've already done it here. So we've said Na equals, Na has this relationship with the radial position. And what may be suitable for us is to, instead of choosing some arbitrary R1, let's choose the surface of the particle. So we can say at radial position R0 there. So this is our Na. And so we can rewrite this equation like so. And the reason we are doing this is because we want to isolate out that R, right? Because you see, when we write it like this, we don't know how to solve this as yet, because Na, according the way it's written here, it's not obvious to us how this is a function of R. So now that we've done some work on that above here, we do know how Na varies with R, so we can just substitute that there. So now this is a specific Na. This is Na at position R0. So let's write this as Na0. just to make it obvious that that's a constant now. And then we do have an R function here. We've got the 1 over R squared. So now this equation is in an easy to integrate form because we've got XA and we've got R. So all our variables are explicit there. They're not implicit the way it was before. So let's just separate the variables and integrate this. Well, I'm not sure. Maybe I can stop there because we have done a problem with R. So I think last time we did a problem where things were changing in the radial direction, but it was without reaction. So now we've developed a similar expression, this time with the reaction, and we've gotten it to the same point now. So the reaction has affected us in terms of what we have here. So you can do this integration. In fact, in that solution, in the online version of the question, the full calculation is shown there as well. Okay, any questions or comments there? Okay, sorry, 1 second. Sorry about that. Please go ahead.
Yes, sir. In terms of R naught squared and R squared, I just wanted to know what those values are. So for R naught squared, would it be 2 millimeters or would it be that 5 centimeters?
So we've said that this is the 5 centimeter diameter particle. So your surface radial position is 2.5 centimeters. Right? So you've got a particle that's 5 centimeters. So and if we are, so that's a 5 centimeter particle. When we say 5 centimeter particle, we mean this 5 centimeters like this. So if R is your position from the center, then this is 2.5 centimeters, right? So that's there. And then the other thing we have in this problem is we are told that 2 millimeters from the particle surface, the mole fraction is this value. Okay, let's keep going with this then. So let's solve this whole problem, and we can rewrite this as, so we're going to move the dr, we're going to integrate in R on that side. There's nothing here that's explicitly in R, it's on this side. And then we're going to move this to the denominator on the right-hand side here. Right, and so now we've separated all the variables, all the R's on this side, all the X's are on that side. And the integral of 1 over R squared is minus 1 over R. So when we integrate this, we'll get minus 1 over R. So that's integrated now. And we are integrating between 2 specific points, right? So we are going from the surface where R equals R naught. And we are going to some arbitrary radial position we haven't chosen yet, R. Yeah, it's a little bit confusing that R, the variable, is here and R, the limit, is there. So normally we use a dashed, or normally we just leave it also. So just understand there's a difference between this R and this R. This is some radial position. This is more like a variable. Yeah. And then if you integrate this, this is the ln of 1 plus 2xa. So we can say ln of this thing. The brackets. Ln of this, and then it's a 2, so we need a 1 over 2, so we need to divide by a 2 here. Let's do it like that. Right, and we've integrated this. So this is between limits at the surface. So this is going to be x a naught, and at some arbitrary position r, where we define the mole fraction to be xa. Yeah, this is like you're getting a free tutorial on using the equation editor. Yeah, so all these keyboard shortcuts make it easier. So that's the general form of this equation. And let's see, well, we still need to write this. At R, it looks like this. Well, let's just get rid of the signs so you can cancel on both sides. So over here, you can write this as, you can see at the upper limit at R, then this is R naught squared over R. And then at the lower limit, this is R naught. So this is going to be minus, so it's R naught squared over R naught. So this is going to be R naught. So that's the first part, that's the left-hand side. And then on the right-hand side, this is ln of the ratio, right? When you subtract ln of something, then you can take that to the power -1. So this is the ln of this at xa divided by the ln of this at xa naught. Okay, so that's, oops. So that's our general form of the equation. We can use this equation to determine xa for any position r, right? We just stick r in here and we can solve this equation for xa. But we do need na naught. That's something we don't know as yet. Now, that's why we are given this extra point. So we are told at this specific, we are given this oddly specific piece of information. So we can interpret this to mean that at that xa, that we happen to know xa at a particular radial position. So this radial position is 2 millimeters from the particle surface. So the particle surface is at 2.5 centimeters or 25 millimeters. And then we are looking 2 millimeters above that surface. So that's +2. So 25 plus 2 millimeters, right? So that's 27 millimeters. So the mole fraction of xa, the mole fraction xa at 27 millimeters is 0.65. And you see that gives us a nice piece of information. We can just stick 27 millimeters in here. C and DAB are given. XA is now this 0.65. And then XA naught is something that's not stated explicitly in the question. So maybe you can tell me, what value would you use for XA naught? Any takers? XA naught equals?
So it says here that there's one, that while the mole fraction at the surface is estimated to be just 0.05, so it would not be xa naught is 0.05.
Does it say that there? Let's see. Okay, yeah, while the mole fraction at the surface is estimated to be that. Yeah, so that's right. That's what you can use. If the problem doesn't give you that, I didn't realize that it was given. If it doesn't give you that, then what you would say is, I'm assuming that this rate is high enough, right? Or sometimes I do say it that way. Sometimes I'll say the rate is high. So when we say the rate is high, that means that A is the rate of arrival of A is slower than the rate of consumption of A. In other words, A is consumed fast enough that the renewal rate by diffusion to the surface doesn't kind of meet that in time. That means surface concentration can be approximated as 0. So it's approximately 0 if your reaction rate is high, right? So whenever you see reaction rate is high, that means it's so high that your rate of transfer doesn't keep up with it, and your surface mole fraction goes to approximately 0. In this case, of course, it didn't say it's high, it said it's 0.05. So yeah, you would use that value there. Okay, so everything is then defined. XA and XA naught are defined. All this is defined. R and R naught are defined. So you can solve for NA naught. So that solves that part of the problem. Okay, so that's the surface flux. And then we are asked, what's the film thickness? And if you recall what we said last time when we did film theory, so according to film theory, your film thickness, which we defined to be delta, your film thickness is defined such that your position XA at the film, so at R equals R naught plus delta, right? Delta, your film thickness, right? So that, in the context of this problem, that's our mole fraction at the film, and that's going to be 99% of the bulk value. The bulk value in this case, I think, is it pure A? A diffuses to that. So if you are not told what the bulk mole fraction is, then you would say, well, I assume then that this fluid is pure A. So so XAB is 1. So this is just 0.99. And so this has now defined for us an X. So this is another X position. So now we want to solve this equation for the film. So for the film, we can say that our R value is now R naught plus delta. Sorry, I mean the lowercase delta. So that's R naught plus delta is our R value. And our XA, we've said, is 0.99. HSA 0. And now we have everything again to solve for delta. This time, delta is the unknown. We don't know how thick this film is. We can use the same NA naught, right? The surface flux is not going to change, because if you think about this problem, we are looking at the same situation. It just so happens we have this extra measurement 2 millimeters from the surface. So we can use this fact to estimate NA naught, right, which we've already done in the first part of the problem. And then it just so happens we ask after that, so what's the film thickness? So it's the same situation. So NA naught has not changed. That's what I'm trying to say. So it's the same NA naught. And then we've got some updated numbers here. And then the only thing we need to solve for is delta there. And then we said in the theoretical development last time, Kc equals dAb over delta. So our mass transfer coefficient we can obtain by taking dAb, which is given, and the delta, which we've solved for in this equation. And that's it. That's how we get our mass transfer coefficient. Okay, any questions or comments there? Right, so I know that's, yeah, we are at the end. Yeah, do spend some time. Like I said, I do want you to think through, how would I solve this problem? So on Wednesday, we'll cover this problem, but Read through it carefully. Think about what we've learned here. We can convert molar flow rates by multiplying molar fluxes and areas. So think about, can I use that to develop an equation that describes how my concentration is changing across the space? So what we want to get to next is developing differential equations that describe how our concentrations are changing. All right. Any questions or comments in closing?
So I just want to ask, will we be going over question 2 and maybe 3 in our next lecture?
Yeah, on Wednesday. We use all these sessions interchangeably between theoretical development and tutorials. So yeah, we'll get to these in the next session.
Say,
Yep.
Can I write you an email after this regarding my problem? Because I won't be wasting other students' time here, because I think I have a serious problem, sir.
Okay, no problem. Go ahead and
I'll
write.
write you an email.
Okay then.
Thank you.
Okay, that's it for today. Thanks everyone. See you next time.